Okay, so we're going to work on the M2 MEI paper from 2015, and we're going to start with question 1. A thin uniform rod JK of length 1.2 meters. Uniform, so the centre of mass is in the middle. It's got weight 30 newtons. Point J on a peg. And then there is a force. Now it says it's rough, but I'll call that one RC. Call that one RP. There's the peg. JK. And this is 0.4. Diagram 0.6 is up to there. Okay. Force on the peg on the rod. So moments about J 30 times 0.6 equals 0.8 times RC. So RC equals 22.5. Force is vertically. All moments about a different place, but RP plus RC equals 30. Therefore, RP equals 7.5 newtons. That's part 1. Part 2. A small object of weight W is attached to the rod. Okay. Find the greatest value for W for which the rod maintains its contact at J. So we want when RP equals, and if we take moments about point L in the middle there, then we've got 0.2 times 30 is got to equal 0.4 times W. W equals 15 newtons. That's part 2. Part 3. The object K is removed. The picture shows the rod resting on the cylinder with its end J on the floor. Some friction force friction force. That's the point K. S, and 30 newtons. The floor is smooth, so hence there's no friction there. It's 0.3, it's still 0.6. Find S, find also an expression for in terms of theta for R and F. So let's call this point L again. Moments about L. So 0.9 cos theta S equals 0.3 cos theta times 30. So the cos theta is different, disappear, and we get S is 10 newtons. And then we'll either go for horizontal and vertical, or we go for parallel and perpendicular. Given we want what R and F are, I'm going to go for parallel and perpendicular. So parallel to the rod, we've got F plus S sine theta equals 30 sine theta. So F equals 20 sine theta. Perpendicular to the rod. R plus S cos theta equals 30 cos theta. R equals 20 cos theta. There we go. They seem like a very easy 8 marks if you can spot them, but hard if you go round and round the houses trying to find them. Okay. Determine the relationship between mu and theta. Well, the friction is less than or equal to mu r. theta is less than or equal to mu times 20 cos theta. So tan theta is less than or equal to mu. There we go. And that was part 4. Let's go on to question 2. So got a block, 8 kilograms. Kilograms. This is Q. This is P. This is 30. Assuming the string remains taut, find the change in gravitational potentiality of the system when Q descends h meters. So assume GPE equals 0 at start, GPE after Q descends h meters. Well, we've got some gain in potential energy, this one, so it's moved h along here. So in terms of its GPE, it will have gained h sine 30 m mg h, and it will have lost 10 g h. So loss this is 4 GH, so it's a loss equals minus 6 GH, loss of 6 GH GPE. Object P makes a smooth contact with the wedge. The system is set in motion with the string taut. Find the speed at which Q hits the floor if A, the system is released at rest with Q a distance of 1.2 above the floor. So energy at the start equals GP is 0. Initially it's at rest, and initially the energy at the start is 0. energy at the end. You've got a half m, which is 18 v squared, and you've got some negative GPE. So we've got 9 v squared equals 6 times 1.8, 70.56. So V equals exactly 2.8, which is always an indication that you're on the right lines. Okay. Part B. Instead, the system is set in motion with Q a distance 0.3 above the floor and P travelling down the slope at 1.05 meters a second. Energy at the start. Is half 18 squared .3. So we're just looking at the start and the end points. So we add those together so that they're equal to each other because there's no external forces. So we've got a half times 18 minus xg times 0.3 equals a half times 18, 1.05 squared. 9v squared equals V equals 7/4 or 1.75 meters per second. Okay, part 3. The slope face is roughened, so the coefficient of friction between the object P and the wedge is 0.9. The system is set in motion with a string taut and P travelling down the slope at 2 meters a second. How far does it move before it reaches its lowest point? Well, we're going to continue to do this by energy, but there's now some energy lost to friction. Energy at the start equals a half 18 times 2 squared. So the energy at P lowest point means that this time actually Q has gone up, so it's the opposite. We've got 6GH positive at that point, and we've done some work done against friction. So at the start we've got 9 times 4, that's that energy, less the work done against friction, which we're going to need a little diagram to explain. So we've got 8 there, so that's 8, there's my 30, so there's 30, so that's 8G, so this is 8G cos 30, so that's R, and F max, it's moving, it's maximum, so it's mu, which is 0.9, times R, which is 8G cos 30, times the distances travelled, which is h, and that equals 6GH. So 36 equals, let's do 6 times 9.8 plus 0.9 times 6 times 9.8 plus 0.9 times 8 times 9.8 cos 30 . 36 divided by the answer, h equals 0.300 meters. Determine what happens after it reaches its lowest point. It's down here. So after it reaches its lowest point, there is a tension here, due to the fact that you've got a 10 kg weight here, and this is wanting to pull it uphill, so we've got a resistive force here equal to mu R tension So let's look at a system. Let's see whether it does move up. So let's do F equals ma in that direction. So we've got mu, so we've got 10g in that direction, minus 0.9 8g cos 30 minus 8g sine 30 equals the mass 18a. Let's work it out. N times 9.8 minus 0.9 times 8 cos 30 minus 2.3. Therefore, A is negative therefore will not move as F not a maximum. And then finally, calculate the power of the frictional force acting on P in part 3 at the moment the system is set in motion. So power equals force times velocity. The frictional force is 0.9 times 8g cos 30, and the velocity is 2. Power is 122.2 watts. So, question 3. Find the centre of mass of this object here, which is a square A with a 1 by 1 cut out. So, centre of mass times the area of the whole lot times the density constant. That's not totally necessary, but it's good to indicate that you know what you're doing, equals the centre of mass of the A squared, which is A over 2, times the A squared, minus the centre of mass of that one, times the 1 squared. And there's a row in there and the row in there. So we get rid of all the rows, and x bar a squared minus 1 equals a cubed over 2 minus a half. So x bar equals a cubed minus 1 over 2 a squared minus 1. By symmetry, because it's exactly the same in x and y, x bar equals y bar, therefore x bar equals y bar equals, using the result that we've been given, a squared plus a plus 1 over 2 a plus 1, using
result, which you can prove. We're not going to do now, and you wouldn't be required to in the exam if they give it to you. Okay, part 2. Show that the centre of mass of the lamina lies on the perimeter if that is true. So let's go the directly rather than the substituting in way. Substituting in, you've got to show that you can multiply it out, but let's go to it. So we're going to say if centre of mass lies on perimeter, then centre of mass equals 1, because it's not going to equal A and it's not going to equal 0. Therefore it's got to equal 1. So we're going to say 1 equals A squared plus A plus 1 over 2A plus 1. And this is both in x and y, so, and then that's 2A plus 2 equals A squared plus A plus 1. So we've got 0 equals A squared minus A minus 1. So A equals the square root, A is B squared, which is minus 1 squared plus or minus the square root of B squared minus 4AC all over 2A equals 1 plus or minus the square root of 5 over 2. Must be positive. Therefore A equals 1 plus the square root of 5 over 2. There we go. Okay, part 3. Show that the centre in another situation, A equals 4. A particle of mass 1/3 of that of the lamina is attached at vertex B. The lamina with the particle is freely suspended at the vertex and hangs in equilibrium. So mass of lamina equals A squared minus 1, which equals 15. Mass of particle at B equals 5, because it's a third. So let's find the centre of mass of the new lamina with mass. So we're going to go, this will be different, x bar, y bar. So x bar times the new mass is now 20, with the old let's just equals let's just work this out. 4 squared plus 4 plus 1 over 2 times 4 plus 1. So we can just use all of this. 16 and 5 is 21 over 10 is 2.1. So we've got the original x bar is 2.1 in this case. So the mass of the old laminar 15 times 2.1, and in an x direction that's got mass 5 and it's A. So x bar equals 15 times 2.1 plus 5 times 4 divided by 20 is 2.575. Y bar times 20 equals 15 times 2.1 plus 5 times 0. So Y bar is 15 times 2.1 divided by 20. 1.575. Okay, so we can now draw a diagram. So we've got this this shape. Let's draw it nice and big. So we know that this is 4, this is 1. We know that the Y bar is 1.75 and the X bar is 2. So it's over here a bit more. So this is 2.575 and this is 1.575. Okay, and we want the angle between that line and that line. Okay, because this is my vertical AB and AG, that's the one that hangs horizontal, so we want this angle. Well, this angle here is 45. Yeah, because it's across a square. And we know this distance and this distance is 4 minus. This is 2.425. This is 2.575. So we could work out this angle here. Tan of theta equals 2.425 over 2.575. So theta equals 43.28. Therefore, the angle that we want, alpha, equals 90 minus 45 minus 43.28 is 1.72 degrees.